G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening, as the case may be. Let's move my image down. This is Lecture 2. Hope you are studying well, handling any challenges on Earth, and praying for God's blessing. So, in this lecture, I'm going to split it up into two sections so that you're not getting too much all in one hit. So, we're going to do relations, equivalence relations, partitions in the first part, and Cantor's theorem and Schroeder-Bernstein in the second part. So, let's go. So some of this you may have seen before in either previous lectures or in school. So bear with me. Here we go. So relations in set theory. A relation R from set A to set B is a subset of the Cartesian product A cross B, which is a set of all possible ordered pairs AB, where little a is a subset of A and little b is a subset of, A belongs to A and B belongs to B. Yep. ARB means A is related to B under relation R. And the order of A and B is important, as ARB may be true, but BRA may not be true. Also, relations can be defined on a single set A where they are subsets of A, so subsets of A cross A. So that's just some general background. So relations properties, reflexivity, ARA, every element A in set A relates to itself. Symmetry, ARB implies BRA. Transivity, if ARB and BRC are both true, that implies ARC, which is pretty obvious. Equivalence relations have all three properties above. So if we've got all three, reflexivity, symmetry, and transivity, then they're equivalent. And again, that's pretty self-evident. Might not be so self-evident when you're just looking at it as little letters, but when you do it in practice, it's pretty self-evident. Functions can be relations where each element in the domain, the first set, can be related to exactly one element in the range, the second set. So, for example, fx equals x squared, you've definitely seen that before, where the ordered pairs are x and x squared. Question, here we go, really easy question for you. Is 4, 2 a relation in the above function fx? Tick tock, tick tock. Answer should be no. Since 4 squared is 16, the relation should be 4, 16. So the order is important. Hopefully you said no. Okay, next one. Draw a 2D graph for the following relations: y equals x squared, y equals x equals y squared, and x squared plus y squared equals 1. So even just thinking about those, you should be able to figure out this is going to be a parabola, this is going to be a line, this is going to be a parabola on its side, and this is going to be a circle with radius 1. So let's draw that. Boom, there we go. Look at that. Great drawing, Dr. Everett. Doing great. Okay, so describe if they are one-to-one, one-to-many, many-to-one, or many-to-many. The one-to-ones are really easy, and if they're many-to-many, that's really easy. It's really getting around the one-to-many and many-to-one is to making sure you get the x's and y's in the right order there. So here we go. Y equals x squared is many-to-one. Okay, many-to-one. So if I make x 2, x squared is 4, so then y is 4. If I make x minus 2, then y is 4 again. So you've got many x's can be 1 y. And so that's really how you need to think of that. Let's go the rest. Y equals x, 1-to-1. That's very, very obvious. And here's the reverse. X equals y squared is 1-to-many. And then you've got x squared plus y squared equals 1. There's our circle, which is obviously many-to-many. Okay? Hope that makes sense. Maybe just take a note of the y equals x squared is many-to-one, and you should be fine. Okay, equivalence relations. There's a lot of different ones we can bring up here. So we'll just go through the rules. If we have a set of numbers, then any number is equal to itself, which is reflexivity. If A equals B and B equals A, that is symmetry. And if And then also, if following that symmetry, if B equals C, then obviously A equals C, which is transitivity. If we look at congruence, modulo n in modulo 5, we'll do an example here. If modulo 5, 7 is related to 2, since 7 minus 5 is 2. Similarly, 4 minus 3, since minus 3 plus 5 is 2. An equivalence class, that might be a new thing. An equivalence class is where you've got all valid values. Now put dot, 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 meaning it extends that way. Probably should have put the bracket around there. Dot, 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 minus 3, 2, 7, 12, dot, 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 going the other direction. So it's all valid values. Okay, you might have a part of an equivalence class, but an equivalence class is all valid values for a modulo. Parallelism, great with the enunciation here. If a line is parallel to itself, that's reflexivity. If a line is parallel to if line A is parallel to line B, then line B is parallel to line A, that's symmetry. And if line, that should be a V should be an F. If line A is parallel to line B and line B is parallel to line C, then line A is parallel to line C, and that's transitivity, which is pretty obvious there. Last image in the way here. Move up. Okay, lastly, any simplification or multiple is an equivalence relation in a matrix. That's great, Dr. Everett. Thanks for sharing. Give me some examples. What a great idea. Let's do that. Okay, so write an equivalence relation, write an equivalence for 306, 033, 093. Really easy because they're all multiples of 3. So, for example, you could have 102, 011, 031, or changing it over, so minus 408, 0, minus 4, 4, minus 12, minus 4, etc. Or, and you can just have an unlimited number of equivalence relations there. Okay, write an equivalence in echelon form for 2, 2, minus 2, 4, minus 3, 10. And so you've just got to give it in echelon form. Echelon form, as a reminder, is just where you put a line down there, down the diagonal, and anything underneath it must be a 0. You don't have to get these into ones. That's nice if you do, but that's not echelon form. Echelon form is just where you've got this number here in terms of 2 by 2. This number here is a 0. If this was a 3 by 3, you'd draw the line all the way down there, and sort of those bottom 3 would all be zeros, and that would be echelon form. So an equivalence relation could be that. So literally just going 4 subtracting 2 times 2, minus 3 subtracting 2 times 2, 10 subtracting minus 2 times 2, which means you're plussing. And so that would be an equivalence relation for that in echelon form. Right, 2 equivalences for 23 mod 30. This should be really straightforward. I've just picked the ones that get bigger by 30, so 53 and 83. You can pick any ones you want as long as they result in 23 when you do mod 30. Write an equivalence for y equals 2x in the Cartesian plane. So if you're in the Cartesian plane, and we just looked at that previously, anything which is parallel to this. So y equals mx plus b is your gradient form. This is the gradient. As long as you've got a 2 there, or if it's moved around, x equals y on 2. As long as you've got a gradient there of 2, you're fine. So really easy. Y equals 2x plus 1, i.e. any parallel line. Okay, next one. Write an equivalence for y equals x squared in the Cartesian plane. And y equals x squared is a parabola. So what we could do is we could have, image just slightly in the way. What we could do is we could have y equals x squared plus 1. Again, it's a parallel parabola where everything's the same. Equally, so this is obviously moving up, moving the vertex up 1. What if we move the vertex to the side? So then you could have y equals, for example, x minus 2 squared. So for these, what I've done is I've borrowed Desmos, which you can borrow at any time you want to. Just Google it. Okay, and what we've done is y equals x squared, y equals x squared plus 1, and y equals x squared, x minus 2 squared, and I've just graphed them. So there's that graph. There's that graph, which is obviously moved up 1, And there's that graph which is moved to the side of +2. And you can see that they are identical. So they are, in brackets, parallel to each other. So they're equivalent. Okay, hope that makes sense. Here we go. Another example. List 5 elements from each of the following equivalence classes. So these are equivalence classes. What do we say about that? Well, I'm only wanting 5 elements, not every single one, just 5 elements from the class. So this is a set 1, 1. So whatever this is, the other one is also a 1. It's also the same thing. So what you're doing is you're making an equivalence class of 1, 1. So possible answer, 2, 2, 3, 3, 4, 4, 5, 5, 45, 45 are all equivalent to 1, 1, are all, no, it's like a subset of 1, 1 in an equivalence class. Okay, now this is an interesting one, and once I've done these two, you'll get your head around it. This is not 2 lots of 1, and therefore this is double. This is just difference. So think of these as difference. So we're going to go 2, 3, 3, 4, 4, 5, 5, 6, 45, 46, etc., etc. So this is difference. It's not like 2 times 1. Don't think that. Again, here 5, 12, and this is making it more clear. The difference here is 7. So if we do that, 2, 9, 3, 10, 4, 11, I've skipped 5, 12 there, 6, 13, and 45, 52. So I've used the 45 there just to hopefully clarify that in your mind that you're looking at difference. Okay? Partitions. A partition of a set is defined as a collection of disjoint subsets of a given set. The union of the subsets must equal the entire original set. This is really straightforward. Definition might be a bit wordy, but once we do one, let's do an example. Given the set X equals 1, 2, 3, 4, 5, 6. What's a partition? 1, 2, 3, and 4, 5, 6. So the union of the subsets, this plus this plus this, must equal the entire original set. So yep, 1, 2 plus 3 plus 4, 5, 6 does equal the original set. So this is a valid partition. Let's look at another one. Another partition could be 1, 2, 3, 4, and 5, 6 again. We add these 3 partitions together. They're disjoint, so they don't overlap. And there's nothing extra. There's like no 7 in there. There's no missing 5. You've got all of them in there. Fantastic. So that's a valid partition. Here's a question. Explain why the following are not, I should have written questions up here, are not partitions of 1, 2, 3. So we've got empty set, 1, 3, and 2. Why is that not valid? Then you've got 1, 2, and 2, 3. That's covering them all. Why is that not valid? Then you've got 1 and 2. Well, that's a bit obvious. Okay, first one, it's not a partition of any set at all because one of the elements is the empty set. So that cannot be a partition. 1, 2, and 2, 3 is not a partition of any set, again, because the element 2 is contained in more than one block. Can't have any overlaps. And whoop, image in the way there, the other way going. 1 and 2 is not a partition of 1, 2, 3 because none of its blocks contain 3. There's a missing 3 there. We haven't got a... Okay? So, fairly obvious. More obvious once you've explained it, Dr. Eric. That's great. That's all we've got. Let myself down here. I'll say God bless you, and I'll see you in part B. Stay safe. You want to have a hot chocolate or a coffee? Or just a glass of water. Okay. Bless you. Bye.